we are down to the last two methods to implement in our singly linked list implementation of the buffer trait in Scala. Those are insert all and iterator. And we'll start with insert all. Though as we'll see, it's actually kind of the more complex of the two. As before, we are going to put a require on our bounds here, except now n has to be less than num_elms plus 1. So the reason for that is because you are allowed to insert one after the last element, and it just appends to the end of the list. Okay, so what needs to happen here? Well, first thing that we need to do is we should probably walk through the list to figure out where things go. Though, I guess if there aren't any things for us to insert, I mean, this is traversable, it technically might not have anything, we probably shouldn't do anything. So let's start with a check. Elms is non-empty. If they didn't give us anything to insert, I'm just not going to do any work at all. Okay? Assuming that there are elements to insert, I need to figure out where they go, and then I could put them in place. Now, either way that so the putting them in place is going to require a loop that's going to go through and build up a list. And instead of actually inserting that list kind of in place properly, what I'm going to do is I'm going to build the new list of elements completely separate of my old list. So looking at a picture here, what I'm going to do is if I were inserting 10, 11, 12 at index, what would this be, 4, I'm actually going to build nodes for 10, 11, and 12 here, and then after I've built them all, I'm going to link that in. So after I've made a list of the stuff to stick in, I'm going to walk through, find the right place to put it, and then insert it there. So our little segment of list, I'm going to start off by making the first element in it. It is a new node of the first element that we have, and null, doesn't point to anything yet. And then I will make a var called last. So I already have a head and a tail, HD and TL. I need different names for these. So this is first element, that is the first new element, and the last new element. And at this point, they're both the same, and this is why also another reason why I had to do the check for non-empty, because this code right here calling head would have been illegal if there wasn't anything to insert. I also want to go ahead and add one to num_elms at this point, because I've just taken one of these elements and I've made a node for it. So let's keep that as part of our count now. Then I'm going to write a little for loop that is going to run through all the elements E in elms.tail. So we've already done the first element. I don't need to do it again, so I call tail on elements. And basically I'm doing an add to the end of the list, which is very similar to what we have with our append up above, which is we can say the last next is a new node of this element E that our for loop has pulled out, doesn't point to anything, and then last equals last next. We've also now created yet another node, so let's increment our number of elements. So when we're done with this, first is going to be a reference to the first node of the new things we're adding. Last is going to be a reference to the last node of the stuff that we're adding. And now we just have to insert that into the right place in our list. And you'll see in a second why we did this first. It's mainly because I didn't want to duplicate this code. Because, as seems to always be the case, there are two broad categories here. We could be inserting at the very beginning of the list, in which case we're going to have to modify the head, or we could be inserting someplace else, in which case we have to walk the list. So I'm going to put a check here for n if n is equal to 0, else I'm going to do something else. So if n is equal to 0, then I can take that last element and set its next to be the head of this list, because everything from first to last is going at the very beginning. Then I can set the head to be first, because that has become the new first element of our list. It's also possible that the list was empty to start with, so I need one of these special cases. If the tail is equal to null, then the tail is last. Okay, so there's lots of these little cases where I have to check, is this the head, is this the tail? I have to do special things, and I kind of want to emphasize that because that'll be significant for the next things we're going to discuss. What if we're not inserting at the beginning of the list? Well, in that case, we do our standard thing where we're going to make the variable I like to call rover, and I start it off at the head, and then for some variable I, we'll go from 1 until n, because we have to stop one short. Rover equals rover.next. What do we need to do here? Well, first, I need to link the last in. And this is one of these things I haven't really discussed much, but when we added the 5 here, we had to make sure that we made 5 point to 6 before we made 2 point to 5. And the reason for that is if somehow we managed to make 2 point to 5 before we made 5 point to 6, I would wind up having no more pointers to 6, and that would be a problem. I often use the analogy of imagine you're on a river and you have a whole bunch of inner tubes tied together. These pointers are what connects the inner tube. If somehow I connect 2 to 5 before I've connected this, 6 and 9 just go drifting downstream and they're gone forever. The garbage collector is going to come and pick them up. So we have to be careful about the order that we do these assignments to make sure that we don't lose some of our nodes. Okay, so now rover is pointing at the proper place, and the first thing I have to do is link in the last. So I'm going to link in the last thing that I'm adding, set its next to be rover's next. Okay, and I have to do that before I change rover's next, because our next line is rover's next equals first. Hopefully you can tell that if I swap the order of these two lines, it's going to have a big impact upon my code, because then I would change rover's next before I use rover's next. That would do bad things to me. Okay, and of course there is also this special case. Well, what if the location that we added was the last thing, so we were appending to the end of the list here? If after this the last next to equals is null, well, that means that there wasn't anything after it, and that means that the last is now the tail. So we set TL to last. And there we go. There's an insert all. Untested, but yeah, there's an implementation of it that would need to be tested. Our last method is iterator. Okay. We've used iterators a lot. There are lots of things, lots of places where iterators appear. There's this iterator type in Scala collection, and it turns out it's a very simple type. It has two abstract methods, a hasNext and a next. We have to build our own iterator that has those two methods in it. So what I'm going to return here is I'm going to make what's called an anonymous inner class. Not what I wanted to do there. Not certain what keystroke I accidentally hit there to pop that window out to the side, but so I want to make a new iterator, and our iterator has to have these two methods. So we have a hasNext, which returns a Boolean, and we have a next, which I'm going to put parentheses on, which returns a type A. Okay, we have to implement those two things. The way to think about iterators are a generic way of walking through lists. If I were doing an iterator on an array-based list, I would wind up storing some integer for the integer index, and I would count up every time. So every time they called next, I'd add one to the index and return a value. Probably would have been the previous value, but implementation details in there, getting that to work. And hasNext would be true until that index had gotten to the end. I don't walk through a linked list by counting I equals 1, I equals 2, I equals 3. I walk through a linked list with code like this. I start a rover at the head, and then rover keeps being set to next. So what I'm going to do inside of here is I am going to create exactly that. I'm going to start a rover, and it's going to start off at head. We have more elements as long as rover is not equal to null. If rover gets to null, that means we passed off the end of the list, and we don't want to keep going. So what should next do? Well, next has to give us back a value, and the first time we call it, it should give us the value for the data at head. So I'm going to create this variable ret that is the rover's data, but it also has to advance us. So I'm also going to set rover equal to rover's next. Okay, so the first time you call hasNext, it'll be on the head, which probably, unless the whole thing was empty, shouldn't be null. So then it can call next. That will wind up advancing it, but before it advances it, it gets the data of that first element and it returns that after advancing. And this can be used in a generic way to walk through our list. And that's the idea of an iterator, is a generic approach to, it encapsulates the logic for going through a collection. We'll wind up writing quite a few iterators from this point on for different types of collections. So it's worth paying attention to how these things are going to work. But in a lot of ways, it is what you would do. You're taking the code that you would have written if you were writing just a normal loop to run through things, and you're taking it and you're breaking it up across this hasNext next type of pattern. So that's it. We've implemented our mutable singly linked list. It hasn't been tested. I leave that as an exercise to the viewer to write test code for this. There are some things I don't like about this, and when we come back, we're actually going to look at an alternate implementation of buffer that I like better. We also need to talk about some of the shortcomings of this particular implementation, not just in implementation details, but in usage.